Part 2 of AP Chemistry Equilibrium is equilibrium constant and writing equilibrium expressions.
Recall from a couple chapters ago that the rate of reaction is proportional to the reactant concentration. Therefore, we can write a rate law for the forward reaction, which is this dinitrogen tetraoxide going to nitrogen dioxide, and we're going to say the rate will be this constant, Kf, times the concentration of the N2O4. We can also write a rate law for the reverse reaction. This is when you have nitrogen dioxide going to dinitrogen tetraoxide, and that rate will be some constant Kr. Kr is reverse, F over here is forward, times the concentration of NO2 squared. The definition of chemical equilibrium, because that's what we're talking about here, is when the rate of the forward reaction equals the rate of the reverse reaction. Therefore, when we're at equilibrium, we just set the two rate laws equal. Okay, so we have the rate of the forward reaction equal to the rate of the reverse reaction. Do a teeny bit of algebra, and we get this expression right here. Whenever we have two constants, it's very easy to make it into one. We just define K equilibrium, the equilibrium constant, equal to K forward over K reverse. And here we have our concentrations divided by each other. So it's a ratio of the products to the reactants. The equilibrium constant expression can be written from a balanced chemical equation. And unlike when we did the kinetics in the last few chapters, now we do take into account the coefficients of each element. So our general format is equilibrium constant will equal a concentration of C raised to its coefficient times concentration of D raised to its coefficient divided by the two reactants. The values are in molarity, concentration.
Okay, so let's look at this example for writing the equilibrium constant for the reaction CH4 gas plus 2O2 gas produces CO2 gas plus water as a liquid. So the equilibrium constant, KEQ, is the concentration of the products over the concentration of the reactants raised to the power of the coefficients. And our equilibrium constants never include pure liquids and solids. So that's why we don't see water here in our equilibrium expression at all. So products over reactants, so we should have the concentration of CO2 on the top, which we do, divided by the concentration of our two reactants, CH4, concentration of CH4 times concentration of O2, and then we should see an exponent of 2 on our oxygen, which we do. So the concentration is raised to the power of the coefficient. So here's our equilibrium constant for this reaction.